This video forms part of the activities of Section 2 of Block 1. In it, we'll be having a look at the landscape of the Isle of Skye and how it has been shaped by its geology. We'll also look at some of the computer software packages you'll use throughout the course. And finally, we'll have a look at the geology and landscape of Dorset. Let's begin with Skye. If we look at Skye on the 10-mile map, then we can see where the different rock types that make up the island can be found. Covering the largest area, and shown in pink, are basaltic rocks, the plateau lavas that were erupted from volcanoes during the early Tertiary. Then we have intrusive igneous rocks, such as the gabbros of the Cuillins, shown here in purple. And in red we can see the granites of the Red Hills. Most of the other rocks in Skye are older metamorphic and sedimentary rocks, onto which the lavas were erupted and the intrusions injected. The red lines on the map are a major dike swarm, running from the northwest to the southeast. These cut through the older crustal rocks and the lavas. When exposed, they sometimes form prominent wall-like features, cutting through cliffs or across the landscape. In Skye, as in most of Britain, the landscape reflects its underlying geology. It's a landscape shaped by the processes of weathering and erosion. And the interpretation of this landscape can give us important information about the underlying geology. Weathering and erosion, particularly by snow and ice, results in the breakdown and removal of rocks, as is occurring here to produce broken rocks called scree on the steep-sided slopes of one of the Cuillin Mountains. Different rock types respond differently to the processes of weathering and erosion. Some, such as gabbros and intrusive igneous rock, weather to produce the very sharp crags we see along the Cuillin Ridge, which itself is almost a knife edge in places. Granite, on the other hand, weathers to produce a more rounded mountain, such as those we see in the Red Hills. Under ideal conditions, such as sunset, you can see where the name comes from, although granite can vary in colour from almost white to this very intense pink colour. Different rates of weathering and erosion are responsible for the variation in topography of the island. Igneous rocks, such as the gabbros, are generally speaking more resistant and tend to form the high ground of the Cuillin Mountains, which are over 800 metres high in many places. Sedimentary rocks, such as limestones and sandstones, have higher rates of weathering and erosion, and so form much of the lower and flatter ground of the Stratheard Peninsula. Near Torrin, Cambrian limestones are exposed along the shore, and at sea level you can find the kind of weathering you might expect in a soft and soluble rock. In contrast, the dike which cuts the limestone is much more resistant to weathering and erosion and stands out. Another flat area of rock in Skye produces the layer cake-like formations of the plateau lavas in the north of the island. Two mountains, known as MacLeod's Tables, show layer upon layer of ancient lava flows. In places, the processes of erosion are spectacularly displayed. On the Trotternish Peninsula of North Skye, the plateau lavas overlie Jurassic sediments, and huge landslips have occurred, such as those of the Korang and Storr. On the Strathaird Peninsula, which stretches southwards from the Cuillins and Red Hills, several of Skye's main rock types are exposed. Its geology, like most of Skye, is dominated by volcanic activity that occurred in the early Tertiary, producing the gabbros of the Cuillins and the granites of the Red Hills. The peninsula itself has high ground in the west, on the hills of Ben Mabost and Ben Cleat, and lower ground in the east. The high ground forms part of the basaltic plateau lavas that outcrop all over Skye. These were erupted on top of Jurassic sedimentary rocks that outcrop on the east of the peninsula, and around Elgol on the west. One of the locations you'll look at in more detail using the computer in Activity 2.2. Both the Jurassic sedimentary rocks and the Tertiary plateau lavas dip gently to the northwest, resulting in prominent scarp slopes between the lavas and the underlying sedimentary rocks. Many of the screes developed along the scarp slopes of the plateau lavas, such as those along the Arncarnach Ridge at the north end of Strathaird, are caused by the faster rate of erosion of the underlying Jurassic sedimentary rocks, causing the harder lavas to break away from the cliff face. Some of the images you've seen in the video are also in the computer software package that forms the second half of this activity. If you're unsure about using a computer, then the next part of this video provides an introduction to the computer software you'll be using in this course. A major part of your time spent studying S260 involves the use of various computer software packages. In Block 1, you'll come across virtual field trips and computer models of maps. In Block 2, you'll use a digital microscope and a digital version of the kit, as well as some software that looks at crystal structures. Block 3 contains some simulations of lava flows, while Block 4 makes use of a computer package that lets you explore sedimentary environments. You'll be guided through your use of these packages in the workbook. In this video, we'll have a short look at two of the software packages you'll use for Block 1, but you'll find the principles involved are the same throughout the course. The first screen you'll see when you look at the software in Block 1 is this one, the block guide. The block guide is merely a small program that acts as your way into all of the software for the block, and there's one for each of the 4 blocks in the course. In it you'll find buttons that will launch the main items of software for the activities in each block, and you'll also find a study comments section that provides some information on where in the course you should make use of the software. We'll start by having a look at a virtual field trip to the Isle of Skye, so we'll launch the program by clicking on the Skye Field Trip button in the block guide. Depending on which block of the course you're studying at the time, the next screen you see may vary slightly. For Block 1, you'll find a startup screen for the particular software package that lists the different packages and the activities in the workbook that they relate to. In other blocks, you may find that you go straight from the block guide to the main software package for that block. This is the startup screen for the Skye Field Trips package, and it lists the 2 field trips, one to Torrin and one to Strathaird. There's also a button to an introduction screen for this package, where you'll find some general background information for the software. To start one of the field trips, we simply click the button. So what are virtual field trips? Well, they're planned in a similar way to real ones, and they give you a chance to explore some aspects of the geology with the help of the computer. Indeed, some of the skills you'll make use of are the same that you'll need on real field trips and at summer school. In many respects, you'll get the most out of them by treating them just like real field trips. And that means first and foremost making careful observations, notes, and even sketches on occasion. Obviously you can't touch the rocks, and though you might feel the need to at times, we don't advise using a geological hammer in your computer. Instead, you'll find that there are various tools that you can use within the software to get the information you need to complete the activities in the workbook. So let's launch the Torrent trip by clicking on the field trip icon. This is the main screen for the Torrent field trip, and you'll find all field trips are very similar in layout, although the information will vary. There are three main parts of the screen: the field trip window, where you view the landscape, the map window that lets you know where you are, and the red dot will give you your current location, and an area across the top of the screen with buttons that lets you move back up to the startup screen, the study comments screen, the help section, or even exit the software altogether. The field trip window is where you will spend most of your time. It provides a means for you to navigate around the virtual environment. Moving around is fairly simple, though you may need a few practice goes to get the feel of it. In particular, much of the information you can obtain is indicated by changes in the mouse cursor. Move the mouse cursor over the field trip window. You'll notice that the cursor changes to a small circle. This is the normal cursor you'll see in the field trip. You can change the view you're looking at by rotating the scene. To do this, press and hold down the mouse button. See how the cursor changes to a small square? Now, while holding down the left button, drag the mouse to the left. When you release the button, the rotation will stop. If you wish, you can rotate the scene through a full 360 degrees. As you rotate the scene, you can see again some of the geological features you've just been looking at in this video. Straight ahead in this view are the gabbros of Blavan, which show up as bright green in the map. If I rotate the scene slightly, we can see the plateau basalts of the Ankarnek Ridge, which show up as pale green. Off to the southwest, we can see the Strathair Peninsula stretching into the distance. And then as I swing the scene round further, past Ben and Duich, we come round to view the Red Hills. And if I click on these, we can see they're bright red and composed of granite. And finally, I can bring the scene back round to look at Blavan again. Okay, so how do you get all this extra information? Well, while you're dragging, you won't be able to get any other information. For that, you'll have to release the mouse button and simply move the mouse around the field trip window. When you're over an area that contains additional information, the cursor will change to small hand with a dot. If you now click the mouse button once, you'll get some additional information, which will vary depending on the field trip. In this case, an information window appears at the bottom of the screen, and the geological map on the left changes to highlight the geology of the area you've selected. Different field trips contain different amounts and types of information, depending on what the activity is. Let's look in more detail at the field trip window. This is one of the views you'll see in one of the other Sky field trips. Along the bottom of the window are several buttons. This one will play a small audio clip, giving information about the location. The other two will zoom in and zoom out of the scene in front of you. On the left-hand side of the window is a locality number, and on many field trips, an Ordnance Survey grid reference. Other buttons will appear when you're looking at additional information. If I rotate this scene to look in more detail at this exposure, then when I click on it, I get a close-up photograph and some additional buttons appear. The information button will bring up a small field note with information about this exposure. As you can see, it suggests that since I'm looking along the direction of strike for these rocks, I measure their dip and strike. Now on a real field trip, you'd need a compass clinometer for this task. Here we've simulated this exercise by providing a small on-screen clinometer that I can overlay on the image by clicking on this button. All I have to do now is to drag it over the image, and then using the arrow keys on my keyboard, rotate it to measure the dip of the rocks. I make that about 10 degrees. Let's make a note of that. To estimate the strike, I'll have to return to the field trip window. I do that by clicking on the return button. Okay, now the field notes said that I was looking along the direction of strike. Well, the compass at the bottom tells me that I'm looking more or less to the northeast. The strata look as if they're dipping to my left, to the northwest. So for this rock unit, I can estimate a dip of 10 degrees to the northwest and a northeasterly strike. You'll find that some localities are rich in geological information, others relatively poor. You can move between them in two ways. In the field trip window, you'll sometimes see a small arrow cursor, a jump cursor. This will do as its name suggests and jump you to the next locality, like so. See how the red dot changes? You can also move anywhere in the field trip by clicking on a blue dot in the map window. That's a brief introduction to some of the aspects of virtual field trips. You can get help at any time by clicking on the help button. To get the most out of the field trips, you should work through the exercises in the workbook. The second type of software package that you'll come across in Block 1 makes use of some computer models to look at the outcrop patterns of rocks as they appear on maps. Here's an example of one that looks at folds, but you'll find the layout of this software the same every time. On the left-hand side of the screen is a geological map. On the right-hand side, a block model that starts off with simple planar strata. This package takes the form of a series of questions that will present a sequence of geological maps and ask you to deform the block model to produce the outcrop pattern that you see. You'll find some of them are quite a challenge in three-dimensional thinking. So how do I deform the block model? On the bottom right, you'll see a set of sliders that let you modify certain properties of the block model. In this case, I can choose between planar strata and two types of fold, and also vary the dip of the strata and the direction of the dip. Let's have a go. I'm going to predict that this is an anticline plunging at 60 degrees to the south. Okay, I've entered my parameters. Let's see whether I've interpreted the outcrop pattern correctly. All I have to do is to click on the Run button. And well, partly correct. The software will give you some feedback, telling you where you've made a mistake and what to think about to correct your answer. Okay, where did I go wrong? Well, it's telling me that I made a mistake with the direction of plunge and with the amount of plunge. In fact, the fold looks as if it's plunging slightly steeper than I entered and plunging to the north and not to the south. Well, now it's telling me I've got the answer within tolerance of the correct answer, and if I click on the answer button, I can see what the true answer is. Well, not bad. Overall, the software will give you 3 goes to get the answer correct, and then you can look at the correct answer by clicking on the answer button that will appear instead of the Run button. You can run this software, which is part of the Map Explorer package, as many times as you like. Each time the set of questions is generated randomly, so you won't see exactly the same sequence of questions twice. You'll find examples of simple dipping strata, outcrop patterns across valleys, folds, faults, and combinations of faults and folds. Well, that's a brief introduction to the software. Now have a go at it yourself. For the final part of this video, we'll look at features of another landscape, that of the Dorset coast in southern England. In Dorset, the landscape is shaped by a completely different underlying geology to that of Skye, and you will see that we'll be dealing with a whole succession of sedimentary rocks and their response to erosion. As well as being one of the most beautiful coastlines in Britain, the Dorset coast is also of considerable scientific importance. It's perhaps best known for its variety of rocks and some world-famous fossil localities. but it also has some impressive landforms. These include landslips. This one's at a promontory known as St Albans Head. There are natural arches. This one's at Durdle Door. Between Studland Bay and Poole Harbour, there's a marvellous beach and sand dunes. In contrast, other parts of the coast have impressive sea cliffs, like these at Warbarrow Bay. And inland, a rolling landscape of hills and valleys. At ground level, it's difficult to make out any pattern to the landscape, but from a higher vantage point, and looking east, you can see that the hills terminate in a distinct ridge that curves across the landscape to form a flat top area, and that's cut by cliffs at the coastline. From the air, here's another view, where you can see the ridge curving round towards St Albans Head. Approaching these cliffs from the sea, and this time looking west, you can recognise St Albans Head again. So what clues can we find to the underlying geology of the area? Well, important evidence comes from the stones used in the local buildings. Widespread use has been made of two local limestones. The Purbeck stone, often used in the construction of cottages in Dorset, and the Portland stone, more durable and used for major public buildings. So we might expect that these limestones form an important part of the underlying geology. The white rocks capping the cliffs at St Albans Head show good horizontal layering, that is, they're bedded and are sedimentary in origin. It's a limestone, in fact it's the Portland limestone. Lower down on the cliff is a much softer grey rock that, when wet, resembles potter's clay. Close up, it's very loose and friable. This clay is one of a series of softer sedimentary rocks, mainly clays and shales, which underlie the harder limestone above. Landslips occur when the clays become waterlogged, particularly after prolonged periods of rainfall, and when the sea erodes the relatively soft clays and shales at the foot of the cliffs. This is the Kimmeridge clay, and it's much better exposed a few miles to the west of St Albans Head, where it forms the cliffs and shore at Kimmeridge Bay. Here you find some very fossil-rich rocks among the relatively thin bands of clays, shales and limestones. This fossil is an impression of an ammonite in the Kimmeridge Shale. And here's another example of an ammonite fossil, which occurs in one of the limestones found in Dorset. Spectacular, isn't it? The difference in the way these rock types erode, a mixture of soft shales and limestones, overlain by a much harder limestone, is responsible for much of the scenery of Dorset. Flying north from St Albans Head, we see that the limestone plateau has been eroded by the sea, producing the present-day coastline, and by rivers which have cut these steep-sided valleys. A little further north still, and then to the west, the topography changes from the plateau to a narrow ridge. You saw this ridge earlier, both from the ground and from the air. Even further to the west, it meets the coastline again, behind the MOD range where the Army has a tank gunnery school. This is called Gad Cliff. Like the cliffs at St Albans Head, these cliffs are composed of massively bedded limestone overlying softer clays. However, here the limestones are no longer horizontal. They seem to dip gently towards the left, that is, towards the west. Only when we get a three-dimensional view of the bedding can we see the true dip direction, which analysis of this aerial photograph shows is to the north. From the air, and with a wider field of view, we can see that there are two ridges of more resistant rock. This second ridge, known as the Purbeck Hills, continues east through Corfe Castle, meeting the coast again at Ballard Down, just north of Swanage. But here we're at the western end of the ridge, at Warbarrow Bay, looking east. And the cliffs of Warbarrow Bay, where this second ridge meets the sea, show it to be yet another limestone, this time a variety called chalk. You'll read more about it in the course unit. This model summarises what we've seen so far. The ridges are formed by the more resistant rock types, chalk to the north, and Purbeck and Portland limestones to the south. Between them is a succession of softer beds, in fact, mudstones and shales. And to the south of the Portland limestone, more mudstone and shale. The detailed geology of Dorset has of course been mapped, and this is the 1 to 50,000 sheet for the area. You'll look at maps such as this in more detail in the next section of this block. They're called sheets. That's because they contain more than just the geological map. Here we have a couple of geological cross-sections across part of the map. And on the right we have a stratigraphic column. That gives us a general representation of the thicknesses of the strata, with older rocks in the bottom and younger rocks in the top. If we look at the geological map, then we can see the strong relationships between the geology of the area and its landscape. A few kilometres inland from St Albans Head are these prominent east-west running rocks, shown in green. If I check the key, then I can see that these are formations of Cretaceous chalk, and they overlie these rocks, shown in olive green, which, according to the key, are the Wealden Formation. These are composed mainly of shales and mudstones that are less resistant to erosion. This results in the chalk forming a prominent east-west running escarpment. The greater resistance of the chalk to erosion can be seen on the coast, where it forms one of the more ephemeral landforms of the Dorset coast to the east, sea stacks, such as those at Old Harry's Rocks. In places on the geological map, we can see that the chalk escarpment is cut by these dark lines, indicating the presence of a fault. This results in an area of weakness in the rocks that decreases their resistance to erosion, with the result that we see steep-sided valleys cutting down through the escarpment. This one divides Ballard Down from the continuation of the ridge at Godlinston Hill. Along the coast, we can see the development of various bays and coves, such as Lulworth Cove, Warbarrow Bay, Kimmeridge Bay, and Chapman's Pool. How have these bays formed? Well, to answer this, let's look at Lulworth Cove. As at St Albans Head, the coastal landform is related to the resistance of the rocks to erosion. In this case, however, there are added ingredients because the rocks are no longer lying horizontally, but have been folded. At Lulworth, a succession of very steeply dipping Jurassic limestones runs parallel to the coastline, presenting a rampart towards the forces of the sea. Behind this rampart are less resistant Cretaceous rocks, and behind these, the chalk escarpment. Over time, the less resistant rocks were eroded either by the action of streams or by the sea breaching the rampart of limestone. Once breached, the less resistant rocks are easily eroded. Well, I hope that's whetted your appetite to learn more about the geology of the Dorset coast. You'll find you can examine much of it with the aid of the 10-mile map.